Hey there, it's Shiyao, working on a CS3 project. How do computers work, you ask? Well, we're just gonna find out. Like, right now. So for our introduction to computer architecture, we start with the von Neumann architecture style. It was created in 1945 by John von Neumann himself. The program instructions and data are stored in the memory unit that is separate from the processing unit. With the von Neumann style, we also have the arithmetic logic unit, ALU. It performs mostly the arithmetic, which is simply just your addition, subtraction, multiplication, division, etc. And it has your logical operations and or etc. With the von Neumann structure, we have our computer subsystems. We have our CPU, the central processing unit. We consider it the brain of the computer since it handles most if not all the instructions that make programs and applications run. It fetches your instructions from the computer's memory, which is the RAM. We'll talk about that later. It decodes these instructions to understand what needs to be done, executes the instructions like performing calculations or moving data around. Essentially, your CPU works very fast and handles everything from running software to controller input-output devices, making the CPU one of the most important components in your computer. Okay, now we have RAM, or random access memory. Usually it's a type of memory that is used to store data and instructions that are actively being used or processed by our CPU. Unlike permanent storage devices like your hard drives or your SSDs, RAM is volatile, meaning it loses all its data when the computer is turned off. So with RAM, we also have our DRAM, stores data in the capacitors that need to be regularly refreshed to retain information, making it slower but cheaper and more widely used for commercial use. Now we have our SRAM, which stands for static RAM. It's faster than DRAM, but doesn't require refreshing. However, it is more expensive and uses more power. Now we have our cache memory. This is a small, high-speed memory that sits between our CPU and our RAM to store more frequently accessed data. Now we have our computer buses, which is a communication system that transfers our data between various components of the computer, such as our CPU, memory, input-output devices, which consist of a set of physical pathways, usually within wires or circuits, and protocols that allow data to be sent and received between these components. In essence, you could think of a bus like a data highway for your computer's components to communicate with each other. Carrying on, we have data buses which carry the actual data being transferred between components. Data can flow both to and from the CPU, memory, or your input-output devices. Also, we have our address buses. This carries memory addresses from the CPU to memory, indicating where data should be read from or written to. And last, we have our control bus. This carries control signals that manage the operations of our CPU and our other components. These signals ensure proper synchronization and dictate actions like whether data is being read or written. Now that we covered the basics of computer architecture, at least in general, I think it's time we should start getting into some machine code. So when you create a program, you're going to use an editor to write a high-level language, such as compiler via Studio to name a few. Now in step 2, it's going to compile the language to machine instructions, and the machine code is read from memory in step 3. And within step 4, the CPU fetches each instruction and executes it. This semester in CS3, we covered MIPS assembly. Essentially, MIPS assembly is a low-level programming language that is used to write programs for MIPS processors. It directly interacts with the CPU, making use of simple instructions that operate on registers. The registers being that it has 32 general-purpose registers for storing data temporarily, for example, from register 0 to register 9. Basic instructions include add, sub, or load word, or store word, or branch if equal, just to name a few at least. MIPS also uses load store operations to move data between registers and memory. So continuing on, we have C to assembly. C is a popular programming language like Java and C++, and a compiler converts a high-level language like C into assembly. A simple arithmetic expression, our x and y, are loaded into a register. The arithmetic assembly computes the expression and is stored into z. Registers are limited, so the computation should conserve registers. For example, in C, a function is named a group of statements that perform a specific operation. A function definition can be converted to an assembly subroutine that assumes register 0 and register 1 hold the argument, and writes the return value to registers 2 before returning. In C, an array is a variable consisting of a sequence of elements. For example, we have the array of 4, defined as 4 elements, accesses arrays of 0, 1, 2, and 3. A compiler is also a program that converts a program into a high-level language like C, C++, or Java into assembly instructions. To wrap things up, we should discuss the input-output structure. Input-output is crucial for enabling communication between the computer, users, and other devices. For input devices allow users to send data to a computer. Generally, your keyboards for typing, your mouse for clicking and moving the pointer, your microphones for recording sound like right now, and your touchscreens on your phones or any other touchscreen device for detecting touch or gestures. For output devices allow the computer to send processed data back to the user or other systems. Examples include your monitor, like what I'm seeing right now for displaying this text and the script that I gotta read out of, printers for producing physical copies of documents, speakers, so that way I can hear what I'm hearing right now through my microphone, and projectors, especially projectors in your classroom for displaying visuals on a large screen. So within our same topic, we have memory-mapped I/O and MIPS assembly. Regions of memory are reserved to communicate to hardware devices. MIPS interacts with other devices by reading or writing to memory addresses. Devices are mapped to specific memory addresses. And lastly, we have syscalls in MIPS assembly. I/O operations are handled by system calls. System calls are predefined structures provided by the operating system. Syscalls allow programs to rely on the operating system to do complex tasks. Registers such as V0, A0, A1, and V0 combine well with the syscall function to carry out these complex tasks. Note, you must execute each syscall by simply typing syscall after a syscall operation is used. So thank you guys for watching, or whoever's watching this. Personally, I want to give a big shout out to my team here. We really tried, we gave it our all, honestly. We want to explain so much more and everything else, but time decided to just be a difficulty, so in the end, we really hope you enjoyed watching this and everything else. I just want to say just good job to you guys out there and everything else, you know. I really enjoyed CS3, and I'm really excited for where it takes me next. So there's that, yeah. I don't know what else to explain, but yeah. Just thank you for watching, you know. Later.